Hello everyone, today we'll be looking at Step 1 2012 question 11. Okay, so the first part of the question is your typical kind of mechanic problems in A-levels where you resolve forces for individual particles, form three simultaneous equations, and then you can combine them to find the unknowns. Okay, so that is in itself not so bad. So here I've already labeled the equations, right? Label all the forces, and we need to formulate essentially an equation for each of them. Okay, and one more thing I need to do really is to label the incline. So I'm going to label the left incline as theta, label the right incline as alpha. Okay, and so let's consider particle A going up the plane. Okay, so we know that well, since it is in equilibrium, all the force going up parallel to the plane is going to be equal to all the forces going down parallel to the plane. Okay, and so we can write that T is therefore equal to 5 mg sine theta, which is the component of the weight that is parallel to the plane, plus 5 mg mu cos theta, which is friction, where mu is a coefficient of friction. And you could do that for similarly particle B. T is equal to 3 mg sine alpha plus 3 mg mu cos alpha. And then finally for particle P, we have that two tensions is equal to capital Mg. Okay, so here's your three simultaneous equations. Now we're given that what theta and alpha are actually. So we know that arc theta is equal to arctan 7/24. Okay, so that means well, if we sketch a right angle for theta, this is 7/24, and then therefore the hypotenuse must be 25. And so from this right angle triangle, we could derive what sine theta and similarly what cos theta are. And so you could do the exact same thing with the alpha. Alpha is arctan 4/3. Okay, and so the exact same thing. In fact, this one is a little bit easier. 4/3, and then so we have our Pythagorean triplet. And so now where you can work out what sine alpha and cos alpha are. Okay, so now the rest of the question, part one, I'm not going to go through, but once you substitute all of these equations for sine theta, cos theta, sine alpha, and cos alpha in, and then and combine equations, solve for mu, and then solve for capital T, and solve for capital M, and you should get the result. Okay, so the results follows. Okay, so let's look at part two. That's what we're interested at. So this time, in the case that capital M is 9m, okay, so let's put that in our drawing. Capital M is 9m, so the weight is 9mg. If that is the case, then determine the initial acceleration of A, B, and P in terms of g. Okay. So the thing here to sort of realize is that capital A, B, and P all have different accelerations. Okay, the reason is that capital P is a moving pulley. Okay, so it don't just moves, it also spins, and so that means the strings. So it's not just a string attached to a fixed particle, but the strings are actually spinning, and so there are a bit more stuff going on here, and we can't just use our normal A-level mechanics for this part. Okay, so what about, so if we let acceleration of A be A1, and then similarly B be A2, and then P be A3. Okay, then we can also formulate the very similar equations to part one. This time we're going to make sure we use F equals to ma, And remember that mass times acceleration. Okay, so so I'm not gonna explicitly write that down, but if you do compare, you should obtain the equation 5ma1 is equal to t minus 3mg. Note that we're gonna take the mu to be our previous value, which you should find mu as 1/3. Okay, so we're going to take mu as 1/3 and then resolve forces, and we should obtain this. We obtain a similar equation for A2, and then finally an equation for A3. Okay, so here are three equations that we will obtain. Okay, and our goal here is to work out what A1 and A2 and A3 are. Okay, but what we realize here is that we have three equations, but we have actually four unknowns. Okay, so we have capital T's as well as A1, A2, A3. So that means that we can't actually solve this uniquely without having some extra information. And in fact, this is what we're going to try to get. The extra information we're going to get is from the fact that how these A1, A2, and A3 are related. Okay, so first things first, let's let's sketch our particles again. So we got A, B, and capital P. Okay, so now firstly what we could do is that we could let the string of this length be L1 of T, the string of this length be L2 of T, okay, and let the string of this length be L of T, and then we're going to let the height of P from the ground level to be H of T. Now notice that these are all function of T, and we don't really care what that T is, what explicitly that function is just yet. Okay, and so do know that we do model A, B, and P to be a particle, i.e. zero-dimensional singular points. So these measurements it does work. Okay. Okay, so now we have to sort of notice a couple things. Firstly, we're told that the string is fixed length. Okay, so if we let string be length L, well, L is fixed, then L, using this equation, using how we set it up, is equal to L1 plus L2 plus 2L plus some constant. Okay? Now this constant is going to be the part of the string that wraps around P. Okay? And then it's always going to be constant because it's always going to be the same length that wraps around P, because P is not shrinking or expanding. Okay? And we know that capital L is also constant. And so what we can do is if we differentiate this equation twice, we are going to obtain the following. Okay, where the double dot denotes second derivative with respect to time. Okay, and now actually, so we can sort of see what we try to do here. L1, the change of length and L1 is really the speed of A, and so if we differentiate that again, the rate of change of time of L1 is literally the acceleration of particle A, and similar with particle B. Okay. Now another thing we want to talk about is that, well, actually these two ramps are fixed height. So there is another constant we can take use of, and that is L of T plus H of T. Okay, because the height of the ramp of these two ramps are constant, so L of T plus H of T must be equal at all times. And so let's do the same trick. If we differentiate it with respect to time twice, we're going to get the following. Okay, so this means that L double dot is therefore H double dot, sorry, minus H double dot. And so if we plug it into our previous equation, we are going to get the following relation. Now, similar to L1 and L2, h double dot is a rate of change of height of p from the bottom of from the ground level. And so this is actually, in fact, the acceleration of p. Okay? And so we have it, okay? So therefore, the acceleration of p, twice the acceleration p, is equal to sum of the acceleration A plus acceleration B. Or we can say that, well, actually, the acceleration of p is the average of the two other acceleration A and acceleration B. Okay? And so here is our fourth equation. So now what we need to do is that we use our first equation, second equation, third equation, and our fourth equation. We have four equations with four unknowns, so we can solve each of these unknowns uniquely. Okay? Well, we know that they are not a multiple each other, so we can solve it uniquely. Okay? And so, well, again, I'm not going to go through the algebra, but if you do, what you should find is that the numbers are not nice. A is 2 over 11g. Sorry, A3 is 2 over 11g. A1 is 3 over 22g. And A2 is 5 over 22g. Okay. Okay, so this technique here is quite useful when we're considering quite a few connected particles. Okay, when we want to determine the acceleration, when the acceleration are not the same for all of them. Okay, thank you for watching.